Out.
Just a second. It's just connecting. Okay, we are live. Okay, so I would like to welcome one and all, both through the YouTube live channel on the TIFR Platinum Jubilees YouTube channel, as well as the Zoom audience here who have joined us for this edition of the NSF Wednesday Colloquium. So a warm welcome. It's a pretty sunny day, although it's cold, but it's sunny day at the TIFR Mumbai. Just before we start this colloquium by Professor T.P. Singh, I just want to give a brief introduction to the colloquium series. As we all know, the Wednesday colloquium is pretty old, as old as TIFR itself, and it was started by our founding director, Professor Homi Bhabha. And this practice of listening to an eminent expert across various disciplines of science by scientists within TIFR has been the sort of starting point for lots of collaborative ideas, as well as ensuring that all the scientific branches, whether it's physics, chemistry, and biology, actually talk to each other and sort of attempt bigger questions than what the fields specify the questions to be. The original tradition was to have the colloquium speaker physically give the talk in AG 66. Unfortunately, due to pandemic, we are a bit limited and we are doing everything on Zoom. And even though we have our own speaker from TIFR Mumbai, we are going through the Zoom medium today. So let me just introduce briefly. We have an eminent expert amongst us, Professor Tejinder Singh, who is going to speak to us today about why do elementary particles have a strange looking mass ratios. Before he jumps on to his talk, just a little bit I want to say about TP Singh, as we call him TP. Professor Tejinder Singh, he is a faculty in the Department of Astronomy and Astrophysics at TIFR Mumbai. He has strong research interests in sort of understanding and delving into problems of quantum gravity. Also, he is interested in the quantum measurement problem and as well as understanding the foundation of quantum mechanics. With just these words, I would like to welcome TP to give his colloquium, and I hope TP you enumerate us about these mass ratios, and it's a connection to the last colloquium that you gave maybe almost 2 years back. So TP, the floor is yours.
Yeah, thank you, Jyotishman, for your very kind introduction. I will report some recent work done with my internship students listed here at the bottom. Vivan Bhatt from IIT Madras, Rajrupa Mondal from IISER Kolkata, and Vatsalya Vaibhav from IIT Kanpur. So I would like to thank my collaborators for their insights, which has led to some interesting progress in this research program. So here you just showing you something which you are probably quite familiar with. The elementary particles that we know of in the standard model, and their masses are shown in this table. Neutrino, we don't know, we just have an upper bound. The electron, half an MeV, then listed in order of increasing mass. In the up quark, down quark, strange quark, the muon, the charm, the tau lepton, the bottom quark, and the top quark, then you see, look at this top quark, how heavy it is compared to the electron. And now if we just look at the ratios of those masses that you saw, it's those ratios that we are interested in because they don't seem to show any good behavior. So here is the electron shown as 1 unit of mass, a half MeV. So in this table, we have taken the ratio of the masses of the elementary particles, the elementary fermions, with respect to the electron. The top row shows their electric charge ratios. The electron is has 3 times more electron, has the electric charge compared to the down quark. The electric charge of the up quark is 2/3 that of the electron. So it is more sort of simple to write the electric charge ratios 3:1:2, or you can say 3:2:1. So that's good behavior. In the first column, we have the electron, the muon, and the tau all have the same electric charge, 3 in these units. The down quark, the strange quark, and the bottom quark have the same electric charge. This is the generation, right? The 3 fermion generations that you know of. The charged leptons, the down quark family, down strange bottom, and then the up charm and top, and the neutrino, electrically neutral, but not very clear. We don't know what mass values are. So we will not talk much about the neutrinos today. So let's first look at the mass ratios in the lightest family, of which all known matter, most of known matter is made. The down quark is 9 times heavier than the electron within experimental range. This is within the range of the error bars. And the up quark is 4 times heavier than the electron. That immediately, you see this pattern 1, 4, 9. So if you take the square root, it is 1, 3, 2. The up quark has remained unmoved from its electric charge position, whereas the down quark and the electron, this should be an important clue for us as we go on. And another hint already is there that it looks like square root of mass ratios are more fundamental than the mass ratios themselves. But once you take a square root, you are on the same sort of wavelength or the same scale as the electric charge. So this again will emerge later in the talk. We are interested in square roots of the mass ratios. And then you see that this is good, but the rest, everything goes haywire. 207, 3483, 186, 8180, 249, and then here this beast, 340,000. But we are physicists, we believe the world is simple. If you see numbers like this, it only means we don't understand where they are coming from. So in this research program that I've been developing with my students, we are trying to develop a program for quantum gravity and unification in a foundational way. I'll come to that in a moment. But we believe the program has reached a state where we can start saying something about the standard model. And last year I reported the derivation of the low energy fine structure constant in this work. And now the claim is, I will go to this in more detail, just to give you a sort of trailer, that those strange numbers that you see here are to a very good accuracy. When you take the square roots of the ratios, this is what comes up. And hopefully you will agree that these are nicer numbers than what we just saw. So if the down quark was to be 1, then this is 1, 2/3, 1/3 in the opposite order of the electric charge ratios, the square root mass ratios. Then if you have a quick look at these other fractions, the only thing number that they involve, apart from 1, 2/3, and 1/3, is this number square root 3 by 8. You see everywhere it is square root 3 by 8. And there's a reason where this comes from. That's the story. It's just the sort of snapshot for where we are headed or what we'll try to prove in the end. Now, let us come to what is our actual research program. As I said, the mass ratios and the fine structure constant is actually an application. And since we get something encouraging, maybe we are perhaps doing something interesting. What is our starting point? That is to address a foundational issue in quantum theory, that the current formulation of quantum theory, say, just take the Schrodinger equation, IH bar del psi by del t equals h psi. It is approximate because it depends on an external classical time. When you do write del psi by del t, that time is a parameter. It is a classical entity. It's a part of the classical world. The existence of such a time is physically meaningful only when the universe is dominated by classical objects. Newton's mechanics, Newton's law of gravitation, Newton's absolute space, absolute time, then the space-time of special relativity, that of general relativity, curved space-time, macroscopic bodies, stars and galaxies. All this is classical. Classical space-time and classical macroscopic bodies, they go along with each other in a consistent way. But these classical macroscopic bodies are already a limiting case of quantum theory. They need not be there, you see. In the absence of these classical objects, there still ought to exist a way to describe quantum dynamics without referring to classical time. I'm arguing it can be made more technical that the classical time parameter owes its existence to macroscopic bodies. Macroscopic bodies are a limit of quantum theory. And in that sense, quantum theory depends on its own classical limit and is hence approximate. Such a description of quantum theory should be improved. There ought to exist a way to describe quantum mechanics without this classical time parameter. Such a description is also quantum gravitational because I have to give up the classical space-time or to give up classical time, then that means space-time is no longer classical. If it is not classical, it is quantum gravitational. And this is required at all energy scales, not just at the Planck energy scale. This is very important to appreciate. If you take today's universe and if you only had microscopic particles like electrons and quarks, you did not have any macroscopic bodies, you will still need to be able to describe quantum theory without classical time. And this will be a low energy scale. This is not Planck energy scale. In that sense, you can easily see in this picture, quantum gravity is not exclusively a Planck energy scale phenomenon. Quantum gravity is needed whenever there is nothing classical in the universe. The current formulation of quantum mechanics heavily depends on the fact that the universe is by and large classical. So for instance, as an example of quantum gravity, consider the gravitation of a massive object which is in a quantum superposition of two positions. So something like this. These kind of states experimentalists create routinely in their lab nowadays, testing the principle of quantum superposition using macromolecules, large objects, make the object large. So these are not two molecules. This is one molecule in two places. Like suppose you do a double slit interference experiment with fullerene molecules. Then after the molecule has crossed the double slit, it's in a superposition of two states. One peaked here, one peaked here, and these obviously interfere. That's how you see fringes. But if this is a massive object, If it is in a superposition of two positional states, consider a field point X. What is the gravitational field due to this object at this point? We already have a difficult situation. The field is a superposition of the field due to the molecule being here, plus the field due to the molecule being here. So we already have a superposition of two classical gravitational fields. And if you put a clock here, you know that the rate at which a clock runs depends on the gravitational field there. So will the rate of time flow be determined by the position here or by the position here? Because the two gravitational fields are different. So again, we have lost the concept of a classical time parameter the moment we are in a fully quantum situation. So this is an example of what I call non-relativistic low energy quantum gravity. This is of great interest to experimentalists these days who try to create such massive superpositions and then detect the gravitational effect at some field point. If the gravitational field can be shown to be in a quantum superposition, that will be experimental proof for gravity being quantum in nature. So this is not just a academic question, it is very much on the experimental domain. What is the nature of space-time produced by quantum systems which are in superposition? It is non-relativistic. It is low energy, certainly. It is not Planck scale, but this is quantum gravity. Now, it gets more interesting. That's what leads us to the standard model. How about relativistic low energy quantum gravity? So here's an example of relativistic low energy quantum gravity, namely the standard model of particle physics at low energies when described without reference to a background classical space-time. So in other words, suppose these are just electrons. No, suppose this is an electron with which I do a double slit experiment, and again ask for the effect on the space-time geometry. Indeed, the gravitation is extremely small. But as a matter of principle, it is in a superposition of two gravitational fields still, and the flat space-time notion is lost. If everything in the world, if all the particles in the world were in such quantum superpositions, you would lose your classical space-time entirely. And so we are asking now this question of principle. If I had to describe the standard model of particle physics at low energies, it's a quantum system. It is described by quantum field theory and very successfully so. But even there is a dependence on an external classical time. How will I describe the standard model without reference to a background classical space-time? That is the question which we are going to address in the rest of the talk. In particular, we expect that fermions can be defined more accurately on a non-commutative version of 4D Minkowski flat spacetime. Let's read the next line also. This non-commutative version bears the same relation to Minkowski spacetime as the Dirac equation bears to the Klein-Gordon equation. So I call this a spinor spacetime. So let's dwell on this. When we take the square root of the Klein-Gordon equation to write the Dirac equation, we learn much more. We learn about the spin of the electron, for example. We learn how to describe fermions using spinors. But notice, why did I not take a quote-unquote square root of the four-dimensional flat Minkowski spacetime? The way we look at Minkowski spacetime is labeled by vectors. It is not labeled by spinors analogous to the spinor which defines the electron. And we already noticed there is some kind of a inconsistency, a tension, if you try to put quantum systems such as fermions, which are in quantum superpositions, if you try to place them in a flat space-time, we have a problem because the gravitation, even though howsoever small, is destroying that classical space-time. One way to think of it is the point structure of classical space-time should be lost now. In a 4D flat space-time, which we call our space-time manifold labeled by four real numbers, t, x, y, z, everything commutes. X times y is y times x, t times x is x times t. On the other hand, the electrons which are sitting in this space-time, their position and momenta do not commute. So we are going to raise this question, could it be that even at this low energies, if we describe the relativistic standard model on a non-commutative analog of Minkowski spacetime, could that fix the standard model? We don't know why the electric charge is quantized in the ratio 0, 1, 2, 3. We don't know why masses have those particular values. And we don't know several other, the 26 free parameters of the standard model. And the expectation is that this ignorance will be fixed when we go to high energy physics. Maybe there'll be a grand unification, a high energy theory will unify with gravity, and then everything will be nicely fixed and understood there. And then you can do a renormalization group flow analysis, and that will tell us what the low energy parameters are, why the fine structure constant is what. That is all right. It may work that way. But suppose, what if we have missed something, namely, I already pointed out this tension to you that there must exist a way of describing quantum theory without referring to classical space-time. The standard model that we write with using quantum field theory does depend on a classical space-time. Can I try to do better? So that is the goal. Okay, so now we will soon get on to this task of building such a description of the standard model where the space-time is not classical. It is flat, all right, but it is not classical. Flat does not mean classical. That's an important message. So when do I call a system quantum gravitational? Because we have high energy quantum gravity at the Planck scale. We also have low energy quantum gravity. How do I have a quantitative criterion of quantum gravitational behavior, which is independent of energy scale, the criterion? So I have quantum gravity in the infrared, I have quantum gravity in the ultraviolet, and I want a criterion of how to call a system quantum gravitational, which encompasses high energy scale as well as low energy. So it can be done. 1 and 2 are quite
TP,
obvious.
TP,
Yeah,
there is a
yeah.
question. I think there is a question.
Yeah.
Shiraz.
Do you mind a question on your motivation, please?
Go ahead, Shiraz. Yeah.
As you say, if matter is in quantum superposition, because of the gravitational kind of constraint equations, the gravitational field will also be in a quantum superposition. But,
Yeah.
but the simplest, I mean, the way that many people would think of that is that there is a wave functional, both for the quantum, both for the matter fields as well as for the metric. So it's like a wave functional over classical geometries.
Yeah. So what would you perturb around? You mean 4D Minkowski?
It's a wave functional which may have its maximal support near 4D Minkowski, but it's whatever it is. You don't really need to.
Yeah. So what I'm saying is, if the maximal support is around a spinorial description of 4D Minkowski spacetime, I get more information the same way that I get more information from the Dirac equation than the Klein-Gordon equation. That's the claim.
I see. But if the gravitational coupling is weak, the space-time in your wave functional will be pretty near to flat space. So
it will be flat. I'll present a spinorial description of flat spacetime. Gravity is weak, no doubt, but there is no reason to think that it is sitting on a 4D flat spacetime manifold, which is R4. Your R4 is having these commutating points. You see, that's what I'm questioning.
I see, but I just don't see how your motivation forces you to do this, because we just take a gravitational.
Okay, let's do it again. Let's do it again. I have a quantum massive particle which is in a superposition of two position states, but
Yeah.
has a very tiny gravity which is ignorable, but it is not zero.
Yes.
So my space-time now has become a superposition of two gravitational fields.
Correct.
What
With
is
wave functional on the metric. Yes.
Suppose that gravity is negligible.
Yes.
I have wave functions for electrons, say. They are producing a so-called space-time manifold. How do I know it is R4?
Because gravity is so small, the metric will
No. But so no, Shiraz, I can put it another way. If you take classical GR and neglect the gravity of the sources, you get flat spacetime. Fine. But now, if you replace your sources by quantum mechanical sources, I think there is a faith, an assumption that my spacetime still continues to be 4D Minkowski R4 spacetime with no underlying non-commutative structure at low energies.
Okay.
Maybe when you see my third criterion, you will see. All I'm saying is there is a so-called spinorial structure underlying R4,
Okay.
which takes me actually all the way to octonions and SO19. I can't do it with SO13. I have to go to SO19 if I want to describe fermions with this underlying structure.
I'll stop disturbing you, sir. TP. I just want to say that the standard semi-classical way of functioning to produce like a path integral, which includes.
Yes, so Shiraz, my claim is that that is approximate. It is not wrong, but it is approximate. It's missing. So if I, for example, extract information from this claimed non-commutative description, that might, encourage us maybe looking at it more seriously.
It's great to try new things, but I just don't feel that your motivation forces you to do what you're doing. That's how you seem.
Okay, no, I would like to dwell on this. I want to convince you.
Okay.
That if you have electrons in a quantum superposition of states, position states, and if you did not know anything about general relativity, suppose you don't know GR, you only have electrons in superposition of, states. You tell me that in the limit that gravity is negligible, can you prove that space-time is 4D Minkowski? I mean, a more serious question. In which space does this wave function dwell, you see? How do I know that it dwells in R4? I have no proof for that. If it's classical, it lives in R4. But I will prove that if it is quantum, it lives in E6, you see, which is not even a real space-time.
I would set up we can talk later.
When you say a quantum system lives in space-time, I'm questioning that. We don't have a proof for that. The particle lives in physical space. The wave function lives in Hilbert space. So I am saying that I will give another description where I will say that the electron lives in this, exceptional Lie group like E6. Lives meaning I will refine the Lagrangian to have the symmetry of E6. And it doesn't live in SO1. So I would actually say that that's a mistake you guys made in string theory to say that the elementary particles live in SO19, and then you try to compactify the extra dimensions. I don't compactify anything. The extra dimensions are complex. Classical systems live in 4D Minkowski spacetime. Quantum systems live in E6. I never compactify. So that's one advantage I have over string theory, you see.
Right. At the moment, I'm not even talking about string theory. Just semi-classical gravity would be a wave functional for the metrics, which would be largely
There is no such thing as semi-classical gravity.
nice.
I never quantize the metric. Classical gravity is emergent.
So
I never quantize the metric.
this is a great new theory,
I'll
but I
never
don't
quantize.
that your motivation forces you to do this. It seems to me.
Ah, okay. Then
Motivation and
when I say that you have to remove, when I say that you have to remove classical time from quantum theory, you don't agree with that? Del psi by del t equals h psi, that t is a classical parameter. It depends on the universe being classical. I don't want a classical universe.
I don't want to disrupt you. We can talk later. Sorry.
Yeah, okay. Thanks. That this is important because yeah, we have to sort out these differences. Okay. So thanks, Shiraz. I'll probably go on now. Okay. So what is the criterion for a system to be quantum gravitational? First and second are obvious. Length scale of interest is of the order of Planck length. If this is satisfied, the systems will be quantum gravitational. Time scale of interest is of the order Planck time. Uh, 10 to the minus. If this condition is satisfied, the system will be quantum gravitational. So I'm saying if any one or more of these three conditions is satisfied, the system is quantum gravity. The third criterion is where I differ from the conventional expectation that a system is quantum gravitational if the energy scale is of the order Planck scale. So we'll replace that. All subsystems have an action of the order Planck's constant h bar. Because as I argued earlier, if all the systems are just free electrons, no classical bodies, everything will have an action of the order h bar. They will be not classical, they will obey quantum superposition. And then I argue that there is no classical space-time left in the sense of a 4D flat Minkowski R4 if every subsystem has an action of the order h. So notice these criteria for a system to be quantum gravitational do not involve the energy. Now, if a system satisfies 3 and 1 or 2, then it is high energy. Obviously, action order h bar, time scale T Planck, h by T Planck is Planck scale. If 3 and 2 are satisfied, or if 3 and 1 are satisfied, the system is UV quantum gravity in the ultraviolet. But suppose 3 is satisfied, but 1 and 2 are not satisfied. We have low energy infrared quantum gravity of the kind I just described. This I call non-relativistic. No, it can be relativistic, non-relativistic or relativistic, but weak quantum gravity because we are much below the Planck scale. So we are now going to talk about regime 3. Condition 3 is satisfied, but condition 1 and 2 are not satisfied. So we have standard model at low energies, but it is a quantum gravitational system. The standard model, in the absence of a classical space-time, which is certainly a more pure way to describe the standard model. Why should I describe the standard model of particle physics in the presence of other classical bodies? I don't want to do that. I remove all classical bodies, I remove all classical space-time, and yet I want a description of the standard model at low energies. And the evidence that seems to emerge is when you do that, this non-commutative spinorial description of 4D Minkowski flat space-time starts fixing the free parameters of the standard model, like electric charge quantization. So just as the Dirac equation yields more information than the Klein-Gordon equation, because I went to something more fundamental, I took that essential square root. Same way, this description of the standard model, which does not depend on a classical space-time, gives evidence that the reason the free parameters are present in the standard model is because we did not invoke this quantum non-classical space-time, which we should have invoked even at low energies. Okay, so now what do I need to do to build a dynamics which is quantum theory without classical spacetime, both at low energies and high energies. Low energies because that's the topic of interest right now, but we want a theory from which gravitation and quantum theory are both emergent. So as I said in response to Shiraz's question, we'll never quantize gravity. It's a strict no-no. Gravity is an emergent classical phenomenon. We want to build a theory in which Planck length, Planck time, and Planck's constant h bar are the only three constants. So that is the goal. We'll have Planck length, Planck time, and Planck's constant, and everything else is to be derived. Okay, so how do we go about it? It's quite nice and simple. Recall the action principle for a free particle in Newtonian mechanics. So where did we start? We have Euclidean space, the Newton's absolute three-dimensional space labeled by coordinates x, y, z. So the distance element is ds square equal dx square plus dy square plus dz square. This is the distance between two neighboring points. Then I define the position vector of a free particle of mass m. Q is the position vector, and Q has components x, y, z. dq by d tau is the velocity. Tau is Newton's absolute time. So the action principle, as you know, which we vary to get Newton's laws of motion, is half m v square integral. The time integral of the Lagrangian, it gives me the action. We are going to follow Newton, and it seems to take us to places. What we are going to do, we are going to raise this dynamical variable q to the status of a matrix. This is the same thing as we do in quantum mechanics in the Heisenberg picture. In quantum theory also, we make our position and momenta from real numbers to matrices. But there we impose the quantum commutation relation. QP commutator equals IH bar, the Heisenberg algebra. That we will not impose. We will not impose the Heisenberg algebra, it will emerge. So what we'll do is we'll make the Q's and P's into matrices, so that your matrices are operators equivalently. Raise dynamical variables to the status of matrices or operators. So my Q becomes a matrix. Replace physical three space by a non-commutative space. So this I'll come to this octonion. Just this is to remind you where we are headed. So instead of defining a distance element between 2 points in this Euclidean Newtonian sense, our new distance element would be something like, here's an example with a quaternion. A0, A1, A2, A3 are real numbers. E0, E1, E2, E3 are four imaginary units. Just please take it like this. I'll be going in more detail. These do not commute with each other. So I define something like a distance element just by the definition of a non-commutative number system. So we are going to create non-commutative spaces by using non-commuting number systems like quaternions and octonions. More on that soon. So what is my dynamical variable? The Q matrix, which has replaced this position vector Q, now has these matrix valued components. So notice dx, dy, dz has been replaced by E0, E1, E2, E3, which do not commute with each other. And uh, this what would we call the metric variables. Like, if this was curved, if the space was curved, there'll be coefficients here like f of x, y, z, g of, that is the metric on a curve. So now the role of the metric is being taken over by these dynamical variables themselves, the matrix valued dynamical variables. So what happens to dq by d tau? It becomes this object. Again, I have something like a square, which is a velocity, but this is a matrix polynomial, you see. Q bar is a matrix. It is a matrix which has these matrix valued components. It's like I have one kind of a non-commutative geometry. So from Euclidean geometry to Einstein's Riemannian curved space geometry, now from there to a non-commutative analog of a curved geometry. That's the spirit. But we will see that when you do that, you start bringing in the gauge fields of the standard model in the same language. Those fields will also be matrix valued dynamical variables. As I said, since this is a matrix polynomial and I want a scalar, I want a number here, I will take a trace of this matrix and I scale the time where there will be a new absolute time because classical space-time is lost here. Non-commutative geometry gives me, thankfully, a new absolute time to work with. That is scaled by Planck time. The so-called new action principle, I associate a length scale with this so-called, what I will now call an atom of space-time matter. It only has a length scale, no other free parameters, which is in units of Planck length, and the action is in units of Planck's constant. And I have here, everything is dimensionless. LP by L, tau by tau Planck. Q has dimensions of length, and it is divided by c d tau, which is also length, where c is, the speed of light is to be understood as the ratio Planck length over Planck time. It is not a fundamental quantity by itself. Okay, so this is, you see, motivated by Newtonian mechanics. We are now going to a...
There is a question, TP. I think Gautam.
Yeah, please, Gautam.
Yeah, hi, TP. So sorry to interrupt.
No problem.
Yeah, so in the previous slide, you mentioned a situation which is low energy. In, let us say, 1 and 2 are not satisfied and 3 is satisfied. And so are you going to sort of apply your kind of quantum mechanical description to an example situation where because of this criterion 3, conventional quantum mechanics will not do the job, and
yes.
Your new formulation will be needed, and there will be some measurable difference from conventional quantum mechanics.
Yes, absolutely.
Okay.
Yes, you are right, absolutely. So in principle, this action should cover both high and low energy cases. So how do I get to high energies? My Q variables will depart from identity matrices. If Q was, like close to identity, they have something like a low energy situation. So in principle, we'll cover both. Yeah.
So, for example, in the description of gravitational scattering of 2 electrons, there would be some result number 1 from conventional quantum mechanics and some result number 2 from your.
Actually, this is a little. The thing is that you are always thinking in terms of, say, graviton scattering.
Or even static, let us say, Newton's law or something.
Yes.
So there will be perceptible I mean,
Actually,
experimentally measurable
right now,
influence.
my focus is on trying to show that the free parameters of the standard model, which are arbitrary in quantum field theory, are no longer arbitrary. I will fix them
But
as a consequence of this
clearly there
new
will be
formalism.
I mean, measurable consequence of your new formulation, which will be different
From QFT.
from QFT, let's say.
Yeah, okay, let's see how it, I would, for example, I would say that I am compelled to have three right-handed sterile neutrinos, just as a consequence of the formalism. Would you say that is something new? Because in the standard model, they are being introduced in an ad hoc way, you see.
I mean, I would go with just, finding the, let us say, the attraction between two electrons, some sector which I'm
my goal is to not disagree with quantum field theory, but to answer those questions which are not being answered by QFT. At low energies, I have no intention to replace QFT. I want to exactly reproduce QFT dynamics. But say, for example, if QFT does not tell me the mass ratios, I want to know if the extra that I'm doing can give me those mass ratios. That's the spirit,
Right. But the role of criterion 3 is being satisfied or not being satisfied would make a sort of...
the difference that it makes is that the free parameters of the standard model are no longer free. That is the role of 3 from my... So it's like saying, suppose I introduce structure in Minkowski space-time, like, underlying octonionic grid or something, then the very kinematics, even before I go to the dynamics, the octonionic grid is telling me, no, you can't place fermions with arbitrary charges here. Charge gets quantized. So this is a consequence of 4D Minkowski space-time having an underlying structure.
Yeah, no, I understand that motivation of yours, but I'm just saying this criterion 3 would seem to suggest that any new formulation would have some perturbative correction.
I agree
in the smallness of the action. Yeah,
I agree with you. Now the question is that to probe that, well, I probably have to go to Planck length scales, you see. Let's see how.
Yeah. Sorry to disturb.
It's okay. No problem. Yeah. Right. Okay. So now
one question.
Abhijit? Yeah. Please go on.
So you were just saying something about gravitons. I think it could mean, because those we think of as some quantum states in the gravity theory. We compute scattering, etc. I think probably could you just say how you want?
So okay, let me say it in a very straightforward way. In my theory, there are no gravitons. There is a pre-gravitation which is mediated by spin 1 bosons, which are actually the right-handed counterpart of the weak bosons, W plus W minus Z0. When I make a left-right symmetric extension of the standard model, very much in the spirit of Pati-Salam. Now, in the Pati-Salam model, you have right-handed, very heavy W bosons. Instead of W plus W minus and Z0 right-handed, I have 3 spin 1 bosons, which I'm claiming are the precursors of gravity. In the classical limit, this starts to behave as if it's a metric field, but I will not quantize it. The emergent classical limit is as if I had quantized, I would have gotten spin 2 graviton, but I will not quantize it. This is very much in the spirit of, where I started. I don't quantize space-time geometry. I am removing classical space-time from quantum theory.
Okay, thank you.
Yeah, thanks. So just to make this more sophisticated, this last line, So this we don't have to go. This is not the path that I'm following really, but just to give you a flavor that these matrices that I have introduced can be written as a sum of what are called bosonic matrices and fermionic matrices. They're made of what are called even and odd grade Grassmann numbers, and you can you even this bosonic and fermionic matrices are then decoupled further into what will be a pre-gravitation part and the Yang-Mills gauge feat part, where a coupling constant alpha is introduced, and this is where we actually read of the fine structure constant from. So the claim is that this form of the action, which came from opening this last line, the claim is that possibly this describes three generations of the standard model and pre-gravitation. But I'm not going to the dynamics of this Lagrangian. What I am going to focus on is how do I know? How do I know that this describes the standard model? So my fixation now would be on the non-commutative space that I have introduced here. The claim is that this space is very non-trivial. It constrains what kind that space-time. You cannot have arbitrary electric charges, for example. So it's like suppose you set these matrices to identity and you just had a non-commutative grid space. The symmetries of that non-commutative space, which I can also think geometrically, not only will they define particles, they will tell us that those particles have to say the SU3 cross U1 symmetry, say, or a SU2 left cross SU2R symmetry. So that's what we focus on. We ask what is the grid going to do. So this is a quick remark on the Lagrangian, that the universe is made up of many such quote unquote atoms of space-time matter. So this is an STM atom. An electron with all its fields is called the space-time matter atom. It has a bosonic part and it has a fermionic part. So all the fields plus the electron together is described by a special case of this action. Same say for other particles like quarks and neutrinos. These will be assumed to live in that underlying non-commutative grid space, which evolves in this absolute time, this so-called Cohn's time, which is outside of the space-time manifold. The 4D space-time manifold is now hidden in here. It is in here and will emerge as a approximation to this so-called non-commutative space on which this Lagrangian is written. Since I've lost the space-time manifold, I must have something new in the nature of time so that I can at least do some dynamics. And that is this absolute Cohn's time, which is a feature of non-commutative geometries, which I just use. You can say we won't go into that. As I said, I'm interested in this underlying space and what that is doing. When a large number of STM atoms entangle, they undergo a quantum to classical transition. Macroscopic bodies in classical 4D spacetime emerge. This is what I was saying in response to Shiraz, that when a large number of fermions, say, entangle with each other to form a macroscopic body, then this entanglement gives rise to localization and also to emergence of 4D spacetime. My quantum system, like a free electron in flight, it continues to live in this more accurate so-called octonionic or non-commutative space, which actually incorporates internal symmetries also. It's not a space-time. It is a unification of 4D space-time with the internal symmetries, and that is dictated. The structure of those symmetries is dictated by the space of the octonions. So other elementary particles which are not classical, continue to live in the octonionic space, and even at low energy, they are in a pre-quantum, pre-space-time space. So suppose a free electron is in flight. We have a very intuitive, sort of primitive tendency to think that that electron is also living in the same space-time in which classical except that its non-wave function is spread out, but it is in space-time. So I'm questioning that particle, that wave function, is not in space-time. It is in a pre-space-time, which is a combination of our 4D space-time and the internal symmetry space, which is complex. Only when we make measurements do these electrons, say, become a part of our classical universe. Even at low energies, the claim is that a quantum system should be described in this more precise way without you appealing to space. We can describe it on a space-time as we do in quantum field theory. That is also excellent. It's a great approximation. But I'm saying that we learn more if we remove that space-time. So that, as I said, the dynamics can be approximately described by QFT on a classical spacetime, but when we do that, we don't know how to fix the standard model. We don't have a good understanding of why the standard model is what it is. Okay, so what do numbers have to do with elementary particles? We want to now make physical space with numbers other than real numbers, even at low energies, staying flat. We will stay curvature flat, but still the space-time will have additional structure. Okay, this is a very quick primer on these numbers, which are known as division algebras. Okay, so it is known that if you ask what kind of numbers allow addition, subtraction, there are only 4 such number systems. The real numbers, of course, made of natural integers, rationals. So this we all know. This is a division algebra. The next is complex numbers. This also we all know very well. Complex numbers can be used to describe the rotation of a two-dimensional vector, which as you know, I can always write a 2D vector as a complex number, and if I want to rotate it by, say, 30 degrees, I have to just multiply by e to the I pi by 6, e to the I, whatever, 30 is whatever. Multiply by e to the I theta, with theta is 30 degrees, and if you multiply this on this vector, it will rotate. So it was a question for Hamilton in the 19th century, 1840s, how to describe rotations in 3 dimensions. Of course, you can do it with 3 angles, but what is the number system? Complex numbers describe rotation in 2 dimensions. What is the number system I need to describe? Yeah.
JD, this is JD. I just wanted to say that we have 15 more minutes.
Yes,
so,
yes, I know.
That's
yeah, I will speed up now.
Yeah.
I'll speed up. Yes. Yeah. So complex. So he asked, Hamilton asked, what number system will I need which generalizes complex numbers, which can allow us rotation in 3 dimensions? And that is how Hamilton has discovered the quaternions. A quaternion is, it turns out interestingly, not 3 dimensions, 4. So the dimension of the number system is doubled. 1 for real number, 2 for quaternions, 2 for complex number, 4 for the quaternions. I, J, K are quaternionic imaginaries, each of which squares to -1. And Ij and K anti-commute. Ij is minus Ji equals K. And you know this. This is very familiar from vectors. In fact, vectors in 3 dimensions can be described alternatively by quaternions. So there's Hamilton found out the rule how to describe a rotation in 3 dimensions using quaternions. So quaternions, so this vector, the dot product and the cross product can be related to the multiplication of 2 quaternions. So quaternions are, in that sense, familiar. Pauli matrices are related to quaternions, and special relativity you can describe using quaternions. But the octonions have not. They are the last of the 4 division algebras. They are 8-dimensional, and there are no more division algebras. And people over that, octonions were discovered by Hamilton's friend John Graves within 2 months of the discovery of the quaternions. They are labeled by 8 real numbers: A0, A1, A2, A3, A4, A5, A6, E7. E1 to E7 are imaginary units, octonionic imaginary units, and they anti-commute. The multiplication rule is given by what is known as the Fano plane. This multiplication is non-commutative, that you can see here. It's also non-associative. And this so-called Fano plane gives us the multiplication rule. Like, for example, how much is E2 times E3? We can read it out from E2, here's E2, here's E3. E2 times E3, I just go cyclically along the arrows. E2 times E3 is E5. So on any given line, the 3 octonionic imaginaries form a quaternionic triplet. So E3, E4, E5, E6, apply the rule that you would apply for quaternions. E3 times E4 is E6, E4 times E6 is E3, and E6 times E3 is E4. So that's easy, it's well defined. But what is our use for octonions? We know that numbers describe physical space. Real line, you can label it by real numbers. 3-dimensional space is labeled by 3 real numbers, that's R3. The space-time of special and general relativity is labeled by 4 numbers, that's R4. It's just the metric is not Euclidean, it is Lorentzian, and particles live in this space. We want to take this message further and claim that the subsequent number systems also describe space. For example, quaternions, their algebra actually can be used to the complex numbers. Of course, we know from quantum mechanics. Quaternions describe 4D space-time. The Lorentz algebra of 4D space-time is just made really from quaternions. The boosts and the 3 boosts are the 3 quaternionic imaginaries, and the 3 rotations is iota times the quaternionic imaginary. That's proportional to the Pauli matrix. So special relativity space-time, you can say, is quaternionic. Note that, if the algebra is the Lorentz algebra, it does not follow that the space-time is commutative. That is not true, because the quaternionic directions do not commute, yet they define the Lorentz algebra SL2C. Okay, what about the quaternion? This is where it gets, the octonion. This is where it gets interesting. So there is a so-called classification of Lie groups, known as the classical Lie groups. SON, labeled by real number, the matrices, labeled by complex numbers, and the so-called, what is this, symplectic algebras, labeled by the quaternions. Now it turns out, very interestingly, largely because the octonion algebra is non-associative, this classification fails when you go from RC at when you infinite dimensional collection of Lie groups and Lie algebras. In fact, there are only 5 Lie groups associated with the octonions, which have these names G2, F4, E6, E7, and E8. So these groups are very important to us. Their subgroups show evidence for containing the standard model. So what we want to think of is, now suppose I have a 8-dimensional space, for example, here. This is my space, physical space. I would now start thinking, can I describe elementary particles as living in this space instead of Minkowski space-time? And I will put dynamical variables, just focus on what is the octonion algebra doing. So imagine, if you imagine the octonion as a 8-dimensional grid, it has structure. It need not have curvature. It can be flat. It can be a flat space-time manifold, but even then it is non-trivial. It has, so what happens? So a little bit technical I have to get. Given let's the smallest of these exceptional Lie groups, which is 14-dimensional, defined by the 7 imaginary directions of an octonion. Given these octonions, or more especially complex octonions, you can use them to make what are known as Clifford algebras, and from there you can construct spinors. So when we do that for the group G2 of the octonions, this is very generic, nothing special about this particular choices of vector directions. You can make what are known as fermionic ladder operators, which is, these are like raising and lowering operators. If you take their adjoint, which is the octonionic and the complex conjugate, you can make the lowering operators as well as the raising operators. You can then also define a number operator, and I will define this object Q, this so-called charge operator Q, which is 1/3 of this number operator. And I construct states from, as I said, given a Clifford algebra, these are generators of the Clifford algebra. Given generators of Clifford algebra made from the octonions, I can make states, and I ask, what properties do these states have? So this is a unique 8-dimensional basis, and it will be only 8, there will be no more. 8-dimensional basis made from the octonions, and it has very interesting properties. SU3 and U1 are subgroups of the smallest exceptional Lie group G2. This state is a SU3 singlet, and it has an eigenvalue 0 of this operator. These 3 states are SU3 anti-triplets and have an eigenvalue 1/3 of this operator. These 3 states are SU3 triplets and have eigenvalue 2/3 for this operator singlet, and has an eigenvalue 1 for this operator Q. This structure, which was not put a priori, but is deduced as encourages us from given what we already know about elementary particles, to say that I have now constructed one generation of quarks and leptons, because here is the electric charge 0 and it's the SU3 singlet, electric charge 1, SU3 singlet. These look like down quarks, these look like up quarks, and you can construct the antiparticles simply by taking the complex conjugates of these states. This involves octonionic directions as well as the complex number iota. This is a very straightforward derivation of quantization of electric charge. Just from the basis of this construction, because these are using only one creation operator product. These are using 2, these are using 3. This is the so-called ground state, the idempotent, there's no alpha in it. So 1, 2, and 3 and 0 are the only allowed possible eigenvalues of this operator, which we identify with electric charge. There's a U1, the U1 here, which is a subgroup of G2, is actually generated by this number or electric charge operator. We identify it with U1 electromagnetic, and SU3 we identify with SU3 color. So you see what has happened. I'm thinking of this object, octonion. I'm thinking of this as a space. Now this space is coming and telling me that I can, if I try to put, I construct these states from the group G2, they have precisely the desired properties for describing 8 quarks and leptons. That is how, what I was saying to Gautam, you start inferring the standard model just as a property of the physical space, namely the octonions. And you see, this is not high energy. I'm just sort of, in some sense, appealing to the flat space-time grid. So of course, we will ask this question, where will 4D space-time emerge from here? And hopefully we'll get there. So how many minutes do I have?
5 minutes, TP.
Five
Okay.
minutes. Okay, yeah. So I think I've given you the main message that just as I constructed one generation of quarks and leptons of the standard model and their antiparticles, there are reasons to believe that the octonion algebra very naturally implies that there are 3 and only 3 fermion generations. They are described in matrices. These entries are octonions. The diagonal elements are real numbers. So if I have to describe 3 generations of quarks and leptons, I just construct analogous states like these. And I can just put this in this so-called Jordan matrix. And the algebra is known as the exceptional Jordan algebra. It is related to the next group F4. The symmetry group of this 3 by 3 matrix is actually F4. And if you complexify it, if you bring complex numbers into it, now these are real numbers, if you instead consider complex octonions, then the symmetry group becomes the next group E6, which is very interesting because it is the only one of these 5 groups which has complex representations. This 3 by 3 matrix describes 3 generations where you can take the diagonal entries as the electric charge. This matrix has a very important characteristic equation whose eigenvalues, if you put in the elementary particle octonionic description for 3 generations here, use this as the electric charge, 0, 1/3, 2/3, or 1. Solve this equation. It yields certain eigenvalues, which I will come to. But before I go there, I want to say something more about the next Lie group, E6. It appears that one of the subgroup structures of E6 is that it has just the correct symmetry to describe 3 generations of left-handed quarks and leptons, 3 generations of right-handed quarks and leptons, including 3 sterile neutrinos. And the left and the right generation have one thing that is common between them is the 4-dimensional Lorentzian space-time, the one that we live in. So it seems this is very special. The left-hand quarks and leptons obey SU3 color and the electroweak, whereas the right ones, although they are coupled by a Higgs, which is there in the theory, the right-handed extension of the standard model brings in gravity. So here there was a U1 number operator, which I associated with electric charge. Here, the corresponding U1 number operator, we by hand assume that that is the square root of mass in Planck units. So elementary particles get their electric charge defined here, they get this. Okay, I think I'll be running out of time. What did we do to find the mass ratios? We solved the characteristic equation of these 3 by 3 matrices for left-handed elementary particles, where the square root, where the electric charge is the U1 number operator. And when we solve that, we can argue that these eigenvalues and the corresponding eigenmatrices arise because the left-handed eigenstates are charged eigenstates, but they are not mass eigenstates. If you take the 3 states which all have the same electric charge value like here, or for the up quarks like here, and you express them in terms of mass eigenstates, these are the eigenvalues. Now it takes some work. So the same theory also yields the fine structure constant. Again, you see, here's where the number 3 by 8 comes up. It is the magnitude of the octonion which describes the elementary particles. So these Jordan eigenvalues, it seems, have some important significance. And again, note this is the property of the octonion space, which is now doing before we the dynamics. There are constraints emerging. The standard model is emerging. Its charge quantization is emerging. This has also just emerged from the octonionic space. And from the Lagrangian, we can actually conclude that what we call the fine structure constant is actually one of the eigenvalues in this Jordan eigenvalues table, which naturally leads to this as the definition of the fine structure constant as a reasonable agreement with the experiment. And again, and this is very important, you see E square by H cross C. As I said, anything that is order 1 in H cross and Planck length and Planck time is a quantum gravitational phenomenon. So in that spirit, this quantity being order unity in the units H bar, Planck length, and Planck time is actually a low energy quantum gravitational effect. So the fine structure constant in this theory is a low energy quantum gravitational effect. To partly answer what Gautam was asking, what we get, which we already don't, not be anything else. It has to be this. Of course, doesn't agree perfectly with the experiment. There are reasons for that. We can. Okay, now this is a partial story. Yeah.
Yeah, TP, we need to absolutely end now. So if
yeah,
that's
okay,
possible,
this is the last slide.
Yeah,
give me 2 minutes, just 2 minutes. I don't claim that this is the final proof for the mass ratio. Some of it I understand, some needs more work. What is interesting is that the same eigenvalues which gave the fine structure constant also give a demonstrably good agreement with mass ratios, the square root of mass ratios. This is data. This is theory. You can judge for yourself whether it is good or bad. Interestingly, to get this agreement requires us to assume that the neutrino is a Majorana neutrino. If you assume it to be namely its own antiparticle, if you assume it to be a Dirac neutrino, you can see for yourself how wrong these were. D for Dirac. See, 14 is correct, 17. 58 is correct, 171 wrong. 23, 3. It just goes top quark. You see, top is to up. If the neutrino is Dirac, I would get, completely wrong values. So as I said, I need to do some more work to prove that this is what the mass ratios look like. The current result is a demonstration that the same analysis does seem to give some understanding of mass ratios. I'm so sorry, I have to skip some slides. This is the summary. I will. So, okay, let me see. What is the takeaway message? If you describe, I didn't tell you quite how the 4D space-time emerges from this octonionic space, maybe another time. But what is happening in the octonionic space is a unification of 4D space-time and internal symmetries, which are complex valued. That's okay. The extra dimensions don't have to be real. They are complex. We never compactify these extra dimensions. Classical systems descend for dynamical reasons to 4D space-time, but quantum systems continue to live in the full E6 space. That's the message, that even at low energies, there is a non-trivial so-called quantum space-time structure that underlies Minkowski space-time. Thank you.
Thank you, DP. Thank you very much. I would like to sort of invite people for more questions. And before you jump onto the questions, I would like to go back to that slide where you had the mass ratios in under square root numbers. Could you please highlight that again?
One moment, yes.
Yes.
How do I? Okay.
Yeah, that 29, slide 29. Yeah. Okay.
I know.
So this is what you have found out from.
Okay, let's see. What I have found out is the Jordan eigenvalue.
Right.
That is a strict calculation. The Jordan eigenvalues and the related eigenmatrices allow us to express quarks and leptons in terms of only 3 fundamental matrices. This we have done for the left-handed particles. I expect the same structure for the right-handed particles. So, because the right-handed particles are mass eigenstates, what this basically diagonalization means, in a sense, that the charge eigenstates have been expressed as a superposition of mass eigenstates, then it's very reasonable that those eigenvalues should give me mass ratio. So some of them are quite natural, like, strange to down. This is understandable. Similarly, charm to up is understandable. When you come here, it gives the correct numbers, but if everyone can legitimately ask what's going on. So this needs some more work. I know what is to be done. Namely, express both the, yeah.
No, that's it. And I just wanted this slide to be highlighted. Because this will actually, lead to subsequent.
Yeah. So what the claim is that this is those strange-looking mass ratios using these so-called Jordan eigenvalues. The same eigenvalues yield a fine structure constant, and that gives me some confidence that I can start believing in these numbers and trying to understand where this somewhat more involved multiplications are coming from.
Okay, I invite the experts to ask questions. Yeah, Basudev.
A very nice and clear talk. Thank you for that. My question is related to something on your slide 22.
Who is it? Which friend?
This is Basudev. This is
Basudev. Basu, yeah. Hi, Basu.
Very nice and clear talk. Thank you very much. So my question is about slide 22. Well, it was a different one. I think the next one maybe, yeah. No, one after. Yeah, this one, yeah. Say 22, correct.
Yes.
So my question is regarding your choice of these 8 operators out of many more that in principle could be constructed.
Yes.
Okay, so for example, you have alpha 1, alpha 2, and alpha 3. Your neutrino operator is alpha 1, alpha 2, alpha 3, and then the whole thing dagger.
Right.
But in principle, and then you have similarly 7 others. But because your algebra is non-commutative, in principle, you have many more things that you could write down.
Give me an example, Basu.
So, for example, you could write down alpha 1, alpha 3, alpha 2.
That won't give me something new, because you see, this is where, you know, the so-called Clifford algebra CL6. These are anti-commuting. Alpha 1, alpha 2 is minus alpha 2, alpha 1, because this is a Clifford algebra. And alpha 1 square, you know, whatever set has to satisfy.
But my point is simply that there are many more combinations of alphas that I can write down, which would not fit into these triplets or singlets. They would
That
be
is not true, Basu. That is not true. That's not true. Anything you do with these 3.
You have 8 Grassmann operators.
Yes. Yes. So
and you want to count how many combinations of 0, 1, 2, and 3 you can make. That's certainly more than 8. So it's certainly true that these states are a subset of your group, but they certainly don't stand alone.
3 with using just 1. Right.
First, I agree with having only 1. 1, 2, 3 is fine.
If you do 4, I think that will just go to 0. Suppose I put 4 of them, because what is true is that in this octonion algebra, all the octonion multiplets you can make go up to 3. And if you do put 4, that will be re-expressed in terms of 3. There's a theorem, I mean, that is, if you look up Cole-Fury's work, so I certainly cannot put 4. Then maybe that's the question.
My question is not so much about 4, but rather why these combinations? Because I could consider alpha 3 dagger, alpha 1 dagger, which is not the same as any of these.
Yeah, but it will reduce to,
Also, these are anti-commutative.
Anyway, so this was my one question, and if I may ask another.
Because of the keys of.
Anyway, so my other question was simply that you're saying that at low energies also, particles continue to live in this octonionic dimension. So if I calculate any radiative corrections, often they depend on like the dimensions in which the particle lives in. So instead of 3 dimensions, now will I have a factor of 8 in my integral?
No, last time we talked, no, the answer that I gave to you that time was not precise. My understanding has improved. At that time, I was thinking that the electron is living in a 10-dimensional Minkowski space, like SO19. That is when you had this question that, you know, if it was living in 4D as opposed to living in 10D, it will show up in my calculation, right? That's what you are saying.
Right.
Now, what I understand better into my understanding is that if I look at this space of E6, actually it is a complex space-time, so to say. The extra dimensions are no longer, how to say, real numbers, you know. So the SU3 for me counts as an extra dimension, you know, whatever. I don't know how to put it. Like E6, this is the dimension of this group E6. And that is all that I have. And in between, I have this 3-dimensional classical, if there is, you know.
Okay, I'm happy to, maybe we can talk more later.
For an electron.
I think, Basudev, TP's connection has been spotty for the last 5 minutes. Sorry about that.
Yeah, no issues. We can maybe talk later.
Right. I'm not sure if TP can hear us right now. TP? Okay, there are 2 questions, Abhijit and Professor Acharya. Not sure he can hear us. I think just I request all of you to be a bit more patient. I'll just see if I can.
Hello.
Hello.
Yeah, this is Jyoti Singh. I'll give my connection to TP. Maybe you can talk. Can you hear me?
Yes, yes, yes.
Sorry, sorry, I couldn't answer you. I got cut out.
Yes.
Can you hear me?
Yes, TP. We can hear you perfectly fine. Thank you. Basudev said that he would like to talk to you offline, if that's possible. Basudev?
Hey, I mean, I just don't want to take up too much time. That's all.
Yeah. I see a couple of other hands up.
Yes, we will take Abhijit's question and then Professor Acharya.
Hi, Abhijit.
Hi,
Is that okay, Basudev? Basudev, is that okay?
Fine, buddy. Thanks very much.
Thank you. Thank you.
Hi. Yeah, I have a question about this mass ratios, right? I mean, so the reason you kind of expect such a thing to happen, that they come out of an eigenvalue, is because electric charge, the U1 charge, came out of eigenvalues of this matrix, right?
No, a little more precisely, Abhijit. For the right-handed quarks and leptons, also there is a U1, which is very much like another number operator. But now I am perforce defining the eigenvalues to be square root mass numbers. They will again have the value 0, 1/3, 2/3, 1. But when I try to express the charge eigenstates in terms of the mass eigenstates, that is where these eigenvalues which split from the original charge values come about.
No, so my question was, what is the reason, what is the a priori reason to expect mass ratios to appear as eigenvalues of this?
Yeah, okay, good point. Okay, let me fill in some gaps that I did not say. What I did with these eigenvalues and eigenmatrices, I've diagonalized the fermion generation. Now you can ask, what are these? What is the diagonalized thing? What are those eigenmatrices? It is very interesting that these 9 charge fermion, the 3 down quark family, the 3 up quark family, the 3 charge leptons, all 9 of them, for all 9 of them, there are only 3 eigenmatrices. I have to do the similar exercise for the right-handed mass eigenstates, and I expect, this is not yet done, I expect them also to be a linear combination of these 3 basis eigenmatrices. This will allow me to write the charge eigenstates as a superposition of mass eigenstates. Involve ratios of these eigenvalues. This was not clear to me last time I gave this talk to you all. And I agree that even now some of these ratios look funny. Why is there a square of that? But my hope is that when this expressing both the left and right hand eigenstates in terms of this basis eigenmatrix is done, I will have a clean expression of the charge eigenstates in terms of the mass eigenstates with some ratios, with some eigenvalue ratios. That will clearly tell me, I think that is reasonable, because what's happening is all our measurements are at the end of the day electromagnetic measurements. We are only making inferences from measurements using charge eigenstates. So if I want to know mass ratios, I have to express these charge eigenstates as superpositions of mass eigenstates. And that is where I expect these eigenvalues to be playing a central role. Does that help?
Okay, so sorry, this is one more question. So, is there a concrete relation of your theory to string theory? Because you brought up this word. I mean,
Very good, very good.
Relation.
Yes. Okay. The Lagrangian that I wrote, the action principle that I showed you, to my understanding, is really string theory because I have an extended object. This is described by a pair of dynamical variables Q1 and Q2. It is definitely, it can't be a point particle. It is
No, but that doesn't mean it's string theory. It's something. That's what it means.
Okay, it is a dynamics of extended objects,
okay,
which is not quantum field theory. It's a pre-quantum field theory. And the so-called, another point of contact with string theory, that E6, for instance, has 3 subgroups SO19, one say for each generation. So the point of departure from string theory is that I will not compactify these 6 extra dimensions of SO19.
No, not just that. I mean, there are only 2 similarities. Just some things are looking similar. Basically, it's not about. You're far from talking about point of departure.
Okay, I think that's a question of how you look at it, and what. Right. The other important difference is related to what Shiraz asked. I will never do perturbation theory around Minkowski spacetime. The perturbation theory will be done around this octonionic space. So if you want to call it different from string theory, I don't mind. Yeah. I would much rather call it, a refined string theory.
No, I think it's probably not that. Yeah.
It's okay. It's not
because it can be misleading. That's why it's better to call it what it is. That's why I was saying it can be misleading to call it string theory.
Okay.
Okay, I don't know whether you like my way of putting it. I'm saying this is saving string theory, you see. It's making string theory into a predictive theory by modifying.
No, but you are predicting with your own theory, right? Why do you want string theory to be predictive? You can predict with your own theory.
I want you guys to take interest in this idea.
No, but don't use the name just for that, right?
Saying,
yeah, okay.
All right, okay.
These are something that we can have offline discussions more. How the flavor of the theory should be popularized. Okay, so now there is a question from Professor Acharya.
Yeah, hello, TP.
Yeah, hello, Acharya sir. Hello, good evening.
Yeah, good. Yeah, I have questions from the experimental point of view. That is, I see that one of your requirement is neutrino is Majorana type.
Yes.
Okay, so which means neutrino-less double beta decay. We have to wait for the.
Yes, so in that sense, it's a prediction.
Yeah.
You should see.
Yeah.
Yes. Yeah. And more importantly, there must be 3 right-handed sterile neutrinos. Unfortunately, I don't know anything about their masses. The Jordan eigenvalues are telling something, but I don't understand right. So I would say even more important than the neutrino-less beta decay, double beta decay, we must look for sterile neutrinos. They are there.
Okay. And one more thing, you had also mentioned about the dark photon. What are they? Could they be dark matter particle or what?
Dark photon. Dark photon?
Yeah.
My understanding is the dark photon is like a long-range U1 component of gravity, which seems to be well suited for being dark energy. The cosmological constant in this theory is very likely exactly 0.
Okay.
So
it
could be that the dark photon might play the role of dark energy, but that has to be investigated.
Okay. All right. Yeah. Thank you. Very nice talk.
There is a last question that I will take. Omkar
hi. I just
hi, Omkar.
hello. I was just wondering, is there a way you think about things like say the Higgs mechanism and stuff in the standard model where.
Yeah, okay. Very good point. My understanding is very limited. There is scope for Higgs. One way in which might come about is that, when you look at these left-handed and right-handed fermions, the chiral fermions, there is a coupling between them through what is this object you might know, the split complex number. With its square is 1, but the square root is neither 1 nor -1. Omega, the split complex number, its conjugate is minus omega, but its square is not -1, its square is 1. This object actually behaves like a scalar. And this is one possible candidate for a Higgs field. It definitely is coupling left and right. It is doing the transfer of mass from the right to the left. Yeah, and another candidate which I do not properly understand, if you have SU2R, the right-handed analog of the electroweak SU2L, that is where I am claiming there are two Lorentz bosons instead of the right-handed weak bosons. What is the third boson in SU2R? Can it be the Higgs, or is it like the right-handed analog of Z0? I don't understand this. There is definitely scope for Higgs also in the Lagrangian, but its mass, what all it's doing, I don't understand that right now.
Okay, thanks.
Thank you.
Thank you, Omkar. Thank you everyone for joining in for this edition of the Wednesday Colloquium, and I thank TP for this wonderful colloquium. And I would like people who are there to just unmute themselves and give a warm round of applause, because there's something that is not there in the online medium. So if TP could hear a little bit of clapping, that would be great.
That's so kind of you. Thank you. Cheers.
Thank you, TP. And I just wanted to say that this colloquium is also again available on YouTube. And that I just would like to sort of share in the chat. Please put that across and you can listen to this again. The next week we have Professor Debashri Ghosh from the Indian Association of Cultivation of Science, Kolkata, who is going to talk about strongly correlated systems for excited state chemistry. So please join us at 4 p.m. next week for an interesting talk by Debashri. So thank you very much for joining in today.
Thank you for coming. Thanks a lot. Thank you. Bye-bye.
Bye.